Now we'll move away from motion in a straight line to motion in a circle. And while forces cause acceleration in a line, that is, that F is equal to ma. So whenever I have a force on a mass, it causes it to accelerate. That is Newton's second law. Torques, on the other hand, will cause an acceleration in a circle. And here when I say it, I mean a rotational or angular acceleration. So instead of having an object accelerate in this direction, we're going to have an object that's going to accelerate in a circular direction. Well, to say that a circle is a direction isn't really true, right? Because if I think about an object moving around in a circle, this object moves in that direction there, and that direction there, and that direction there, and that direction there. So to call a circular path a direction is not really correct. To really deal with that correctly requires more than we'll do in this class. But just for now, know that forces cause this linear acceleration and torques cause an angular acceleration. Now, that when not rotating, the net torque is equal to 0. And let me define what torque is. We're going to use the Greek letter tau. This is the Greek letter tau. Sort of looks like a backwards J, I guess. And it is equal to F times R times the sine of the angle theta. So if I imagine, I'm going to erase this. If I imagine that I have some object, a bar or whatever, say I have a bar, pry bar, whatever, it rotates about a certain axis. Now, if I apply a force in this direction, let's say that I apply a force equal to 2 newtons, that is the F in this equation. I apply it at a certain distance from the axis of rotation. I've drawn the axis of rotation here. If I have an object that's rotating about a certain axis of rotation, say right here, if I apply a force, that object will then rotate about that axis of rotation, going around from the applied torque. Now, the distance from where the force is applied to the axis of rotation, that is our value for r. This is called the moment arm. It's not a radius. It's sort of like a radius, but we call it the moment arm. And then the angle theta is the angle between the force and the moment arm. In this case, that angle is 90 degrees. And I just want to remind you that the sine of 90 degrees is equal to 1. The sine of 0 degrees is equal to 0. So I'll get a maximum torque from this force, but if I had a force pushing in this direction, I wouldn't get any torque at all. In fact, there are a couple ways to open a door. That is, I can apply a force here, perpendicular to the door. That's the most efficient way to open a door. Or I can apply a force like this, which is parallel with the door. I'm never going to open the door at all. There's another way, by the way, to open a door, and that's to apply a force over here. And there, if you apply a force close to the hinge on the door, it becomes really difficult to open the door. That's why when you see most people trying to open the door, they'll follow this technique, where they apply a force that's perpendicular to the door and as far away from the axis of rotation as possible. The units for torque, because it's F times R, is going to be N times M, or Newton meters. So let's look at this. If I know that an object, if it's not rotating, the net torque is equal to 0, and I know that here, this object is being held in place. I have an axis of rotation right here. I want to know what is the torque required, or what is the force required at the end of this lever. This is a class 1 lever. We'll see those in just a minute. What is the torque required in order to make this thing balance? I'm going to apply a force right here. I'll call that F. I have a force here, F. I'll call this let's call this F1, and it's equal to the weight of this block, which is m times g, or 2 times 10 meters per second squared. That's 2 kilograms times 10 meters per second squared. That's going to be 20 newtons. And then over here, I'll call this F2, and I want to know what F2 is. So I know that the sum of the torques is equal to 0. That is, I know that the torque here has to equal the torque on this side. And then we're going to take a simple approach to this where whatever torque I have on one side, I have to have also on the other side. So I'll call the torque on the left side has to equal the torque on the right side. That is to say, torque L minus torque R is equal to 0, which is, what this equation says, that the net force, or excuse me, the net torque has to be 0. So on the left-hand side, I have F1 times R1 is equal to F2 times R2. F1 is 20 newtons. R1 is the distance from where the force is applied to the axis of rotation, that's 2 meters, is equal to F2 times where the force is applied to the axis of rotation, that is also 2 meters. And so F2, as you probably guessed, is equal to 20 newtons. It's the same as the force on the other side. Now what if, instead of having a force acting at the end of the lever, I have a force here? I'll call this now F2, and I want to know what that force is. So I do it the same way. The sum of the torques equals 0. That is to say, torque on the left-hand side has to equal torque on the right-hand side. It's going to be F1R1 has to equal F2R2. So 20 newtons times 2 meters, same as before. Now F2, if this distance is 1 meter, I want to know what then is F2. Now because I've made the moment arm shorter, I now need a bigger force. So here my force is going to be 40 newtons. Before it was 20 newtons to balance this, and now it's 40 newtons. Twice as big because I've halved the length of the moment arm. We'll see some more applications of torques when we get into levers.